Welcome to this presentation titled Machine Learning Belongs in a Museum. This is a presentation that is part of the Scottish Summit 2024. So you can use the hashtag Scottish Summit 2024 if you are at the event or you are watching this presentation. All right, so we know that these events are not possible without the help and support of our sponsors. So for the online sessions, our online streaming sponsor is Proximo 3. Our digital sponsors are Locodera, Riada Consultancy, and Cubix. So big thank you to all of them for promoting these type of events, and make sure that you check them out. So who am I? My name is Sam Gomez. I am a Microsoft MVP. I have over 15 years of software development experience. I am also a husband and a father of two boys, 7 and 3, and love spending time with them. I am also a big football or soccer fan, depending on where you're watching this. I currently work as a client partner for a software consulting company called Jenica. You can visit us at jenica.com. And you see that QR code at the bottom of the slide where it has all my links to X or Twitter, however you're calling it, LinkedIn as well. I would love to connect with you and have more conversations if today's topic is of interest or you are working on a similar project. At the bottom, you can also see the link for my link tree that has, like I said, all those links available. So the agenda for this presentation, we're going to look at the project. We're going to do a project overview. So we're going to talk about what the objective of the project is, and we're also going to talk about the motivations for this project. Then we're going to move on to what did we do, how did we solve the problem that we had. We're going to look at some of the tools that we use in case that, again, you are working on a similar project or you are just curious about them so that you can check them out. And we're going to talk about some of the lessons that we learned, not on this project, but also in other machine learning projects that we have worked on. So let's get started with the project overview. So today's session is a case study about a project that I worked on over the last year that includes machine learning. So let's talk about what we did. So the objective of this project was to build a process that is backed by a machine learning model and that maintains the temperature and humidity in different areas of a museum. So for this project, us at Jenica, we partnered with a company called Ameresco that specializes in energy efficiency projects. And this project is actually in use right now at the Art Institute of Chicago. So if you ever visit Chicago or you have visited Chicago in the last year or so, the humidity and temperature in different areas of that museum were controlled by the project or the workflow that you are going to see in later slides. So it's really cool. It's really great to kind of have that kind of project where you know that it's being used at the moment and you can actually go and experience that as well. So like I said, if you are visiting soon, just check it out. So what are the motivations for this project? Why did the Art Institute wanted to implement this? First of all, is to reduce carbon footprint. So we know that the environment and being more energy efficient is a big concern for a lot of organizations. That has the consequence of saving money. We know that heating or cooling any space is going to use energy. And obviously, if you're more energy efficient, there's going to be some energy savings. Who doesn't like that, right? And then finally, this being a museum, we have pieces in there that are very valuable. Some of them that are, you cannot put a value into them, pieces that have been around for centuries and not thousands of years. And we need to keep them safe. A lot of those pieces required certain conditions to avoid any damages, like paintings, sculptures, things like that. So that is another motivation to do this as well. Now, let's talk about what the process looked like before this project. So 100% accurate drawing of what that looked like. So the museum has a team of building engineers that are monitoring, or were monitoring, the different areas of the museum. And then whenever they saw a particular area that would deviate from the threshold, from the ranges that was considered safe, they would immediately change that temperature to about 58 degrees. So that was, like I said, a very manual process. They had a team of people looking at this, and they were looking for an automated process for all of this, or a tool that would assist the building engineers with this job. So that system that they were looking at, or that system that they used to monitor different conditions in the building, is there's a screenshot now in this slide. So this is what it looks like. This is what they are looking at to determine whether everything is still working as it should and the conditions are being met. This is called, or this has a picture of an piece of equipment called an air handler. So what this does is just basically circulates the air in a room. So if you're at home, for example, you have vents all over your house that pump heat, hot air or warm air or cool air or cold air, depending on how you're feeling at the moment. And this piece of equipment basically does the same, although it's a little bit more complicated than that, because this piece of equipment can also heat the air. It can cool it. It can remove humidity, or it can add humidity based on the current conditions. It can also pull air from the outside if that is something that is needed. So a little bit more complicated than our AC system at home. But if you go to any other building, chances are there's a piece of equipment like this somewhere controlling all that airflow in different areas of the building. This up here, this value up here that says return air temperature or discharge air temperature, that is the value that we are trying to predict and the value that we are trying to control in this project. So we have the discharge air temperature. That is the temperature of the air that is coming into a room at any point in time. That air also has a humidity value, which is called the discharge air humidity or the supply air humidity. Those terms are used interchangeably sometimes. And those values are going to have an impact on the humidity and the temperature inside a room, which is what we are trying to keep within a certain range. So again, discharge air temperature is the main thing, or the main value that we are trying to predict in this process. Now you might be wondering, well, there is a system already that they're using to monitor. Can this be programmed somehow to manage all those conditions and control that value? And you could do that in theory, but it would be more so you would need a bunch of if statements to try to cover every condition, because humidity and temperature are very delicate and can change by due to a number of reasons. So it's a very complicated thing. You would end up with a limited number of if statements, probably. And yes, there is a joke that machine learning is a bunch of if statements. And a decision tree, it's an algorithm that, yes, it's a bunch of if statements, but those are generated automatically. They're not logic that you have to program by hand, that you will have to update, that you will have to maintain, that you will have to tweak, which would be a very, very difficult task. So that's why we need machine learning in this particular project, because that would allow us to have a more dynamic system that will be able to cover more conditions around the building. So now that we have an overview of the objective of the project and some of the things that we need to know about it, let's look at what we did to accomplish that task, to create that system, to create that process that would be able to control those conditions. So the first thing that we had to do was to evaluate an existing prototype for this system. So when Jenica came into this project, there was already a process running in 5 different areas of the museum. The goal of the project was to expand this to more than 20 areas, so obviously cover the entirety of the museum. So we needed to know if we could reuse any parts, any pieces of this project, because it wasn't performing at the level that the museum required. So again, we were trying to figure out what can we reuse? Can we just tweak the existing process a little bit so that we can get to something more efficient a lot quicker? So that process looked like this diagram. So on the left-hand side right here, we have a system or a software called EasyEdge that was the bridge in between the input from the sensors and an Azure IoT Hub instance. So whenever we got that raw feed from the sensors, it would go through the Azure IoT Hub. It would get stored in a blob storage container, and then a compute would do a prediction. That prediction would get dumped into a different blob storage container. Every time that a file was created or prediction was created, it would trigger an Azure function that would send the prediction value or the predicted value back to Azure IoT Hub, back to EasyEdge, and back to the museum. That prediction was also archived so that we could go back and look at it for reporting purposes or retraining or anything else that we needed to do with that data. Now, going back to this machine learning compute, let's talk a little bit more detail about that. So that machine learning compute was a resource that's running 24/7, and the process inside of that machine learning compute, it was going every 15 minutes, grabbing the last 90 days of data from this blob storage and doing a training to generate this prediction. So there's two main challenges and two main issues with that. Well, actually three. Number one, that compute process or that compute resource would sometimes shut down without us really knowing why. It was a bit of a black box where we couldn't look at the logs and what was happening, or at least not in an easy way. Number two, going to that blob storage that often and getting that amount of data was starting to get the cost for blob storage out of control. Remember, we are talking about only 5 pieces or 5 areas of the museum here. We wanted to expand that to 20. So if the cost was already climbing, it was only gonna get worse. Finally, the process was training or doing a training every 15 minutes. In this type of problem, this type of situation where we're talking about a classic regression problem where we have a bunch of features and we're trying to predict the value, that is not something that you need to do. You don't need to train every 15 minutes. So unfortunately, that meant that the most important piece in this process is the only one pretty much that we could not reuse. So that was obviously a problem, but it was also an opportunity. Since we had to make some changes to this process, we went back to our partners in the museum and we had a conversation about what other things can we change or what other things needed to change to make this process better. So again, we turned that problem into an opportunity. And obviously, the first thing that we had to improve is a better model. We needed to create a model that was going to be more efficient, that was going to allow the temperatures to go higher, because we knew that that was a thing. We also needed separate processes for each air handler, and we needed to be able to turn these on and off very, very quickly. The reason for that is that some of the areas of the museum might hold temporary exhibits, so we don't need to control or be so strict about controlling temperature and humidity in a lot of those areas. Or maybe there's some maintenance going on, some construction or something, and a particular area is shut down. We don't need to worry about controlling the temperature at that point. So we need to be able to turn that off and turn it back on whenever is necessary. Another thing that we needed is also a gradual temperature increase. So we knew that increasing the temperature too quickly, either increasing or decreasing the temperature too quickly, was not going to be efficient for this process. So that's another thing that we had to do. We obviously needed improved logging. As I mentioned, that compute resource that we had at one point was it was difficult to get any sort of information out of it. So we needed a better way to do that logging. And we needed also reporting so that we could know how the model or the entire process was working. And we could do things like submit the information to get some rebates and things like that. So now, since we had to change the way that we were accessing the raw feed from the sensors, there were some challenges that we needed to consider and that we needed to solve. First of all, like I said, it's data access. We're not gonna go back to the storage, to the blob storage, and use it the way that it was being used at one point. We needed to find a different way to access that data. Another problem that we had is that the data points were not standardized. We know we developers are famous for being bad at naming things, and unfortunately, that meant that in this case, the temperature data point, for example, had 2 or 3 different names. So we needed a way to take that raw feed, put it in a common format, so that the prediction process wouldn't have to do any processing with that data. The other thing that we had to consider is that the sensor data or the sensor updates were coming in every 5 minutes, but our prediction process was only running every 15 minutes. So we needed to find a way to also standardize those names and aggregate the data so that only the last value for a particular endpoint, a particular data point, sorry, was available to our prediction process. So those 3 things we had to consider. Now, for the first phase or the first version of this process, what we decided to go is use an API called Asset Planner that was available from our partners, Ameresco, and that API would allow us to get all that data that we needed without having to worry about setting up a separate process. However, that was only available for, like I said, the 5 first areas of the museum. For the other areas that we needed to integrate into this process, we needed to find a different way to capture that information and make it available for the prediction process. So let's talk about that first version that we created. The first thing that we had to fix, as I mentioned, was the model that we were using to generate that prediction. The predictions that were coming out were not as efficient as we needed them. So the values for the temperature were being too conservative. So the first thing that we did is we added more features to that model, or we created a model that would consider more features than the 2 that were used in the prototype. So this is an example of some of the features that we used. We were using the temperature from the outside, the humidity on the outside, like I said, because we are bringing that air sometimes. We are using the CO2 inside an area as to kind of determine how many people are inside a particular zone, particular area. And all that, we were using it to try to predict that discharge air temperature. That is what we are trying to control. Now, this process had a flaw, and we knew that going into it. And the flaw was with the training data. If you remember, when we talked about the manual process, the default behavior from the building engineers was to just move the temperature to around 58 degrees if they saw that a particular temperature or humidity was outside the range. What that meant for our training data was that a lot of the values for the discharge air temperature were around that 58 degrees. So we knew that because the data looked that way, most of our predictions were going to come around that particular value, 58, 60, things like that. Now, the idea was that, okay, let's create this model. Let's have it come out with a prediction. And then we will put some logic after the prediction to kind of increase or decrease the value based on some calculations that we came up with. So once we turn that on, we encounter some issues, like we said. So first of all, big temperature changes. So that logic that we had after the prediction, it was creating increases more over 1 degree. And we found out through trial and error and through creating this process that the biggest change that we could do at the determined interval, so every 15 minutes, we could only increase or decrease the temperature 1 degree. Otherwise, we would enter a cycle of heating and cooling that would defeat the purpose and would not bring any energy savings. We also found that some of the features that we used in that first model were not needed, and at the end of the day was too conservative. The other issue that we were having is that logic that we had after the prediction was, guess what? A bunch of if statements. So we ended up with something similar to this, where we had some machine learning in the process, but that logic, those if statements, were getting out of control. So we were ending up with something like you see on the image here, where it's not machine learning, we're just using a bunch of if statements. So now the idea was that hopefully we could come up with new data, better data that we could use to retrain the model. Unfortunately, that did not work out. Now, one thing that came up or came out of this first version was that we used Azure Functions to implement the requirement of having separate processes for different areas of the museum. So we have one Azure function per air handler. That way we can turn off that Azure function as needed. There's also another reason why we needed separate processes, is because the ranges in different areas are going to be different. Some areas might allow the temperature to go a little bit higher, so we needed to be a little bit more permissive there. We just needed to have all of that separate and configurable. The other thing that we did is we obviously put a ton of logging into those Azure functions. So we are now capturing if we're missing any data. So we want to know that so that we can identify possible issues with the input from the sensors. We want to capture whether we are warming up or cooling down. We also want to capture why are we warming up or cooling down. Is it because of the temperature? Is it because of the humidity? Or is it because of both? And we also obviously want to capture the prediction value. All those things that we are logging have come in very handy when we are doing troubleshooting, when we're trying to find out why is the process behaving a certain way, or why is it not working at a particular period of time. So what that process looked like is we have ECEdge again over here, being that bridge between the sensors and an Azure IoT Hub. We're still archiving that input from the sensors, but now we are using an Azure function that is calling that model that we created. The input from the sensors is coming from Asset Planner for the prediction function. Those prediction results are still being archived. And there's also that function that gets triggered anytime there is a prediction, which sends it back to the Azure IoT Hub and back to ECEdge and back to the museum. So this is what that process looked like. Again, we set up that initial infrastructure, but we needed to go back to the drawing board to create a better model. So that takes us to the second version of this process. And the way that we went is, or the solution that we came up with is to try to predict the humidity in the room. So one thing that we're trying to control is the temperature. The other one is the humidity. We are already getting an initial temperature from the sensor input. So the thought was, let's use that, let's change that or update that value either up or down. And then let's try to predict what would happen if we increase or decrease that temperature. So we're trying to predict the supply air humidity, so the humidity in the air. So if we increase the temperature of that air, what's going to do to the humidity of that air? And in turn, what are those changes going to do to the humidity in a particular room? That's, again, the other thing that we are trying to control. Now, Because of the close relationship between that temperature in the air, the humidity in the air, and the humidity inside a room, we had to come up, or we had to train two models instead of one. One model would try to predict the supply or humidity. Another model would try to predict the humidity value. So the process looks like this, more or less. So we have this model that creates a prediction for the supply or humidity or the discharge or humidity. That prediction is then used to predict what will happen to the humidity. And then based on that, if the values are still within the range, that is the discharge air temperature that we are sending back to the building. So at a high level, what does that look like? So we get the current measurements and we determine whether the humidity and the temperature are within the range. That is going to tell us if a particular area is too hot or too humid, then we need to decrease the temperature. Otherwise, we can increase it a little bit. So once we've made that determination, we come over here and we try to predict the supply air humidity, so the humidity in the air. So let's say that we get the current temperature of the air is 60 degrees. So if we increase that half a degree, so if we increase that to 60.5, what would be the humidity in that air? And then with those two values, so the new temperature and the new humidity for the air, what would happen to the humidity in the room? What would be the new value for the humidity? If those values hold, or those values are still within the range, then we repeat that process. We increase another half a degree. If those values are predicted to be outside of the range, then we just send the last value for the discharge air temperature. So if this value is 60.5 and it's still within the range, then we try again. We try to increase another half a degree to 61. And then we do the same prediction and we do the same check. So if 60.5 stays within the range, then we send that. If 61 stays within the range, we still send that value. We do not increase more than 1 degree per interval. As I mentioned earlier, that is what we found, that's as much as we can change every interval. It doesn't sound like a lot, but once you are interacting with all these different things of people within the room, the air in the room, and all ton of other factors, that's how much of a difference half a degree or 1 degree can make. So high level overview of what that prediction part of the process looks like. This is an architecture diagram of that second version of the process. So now we expanded this to other areas of the museum. So you'll see here that there's two different ways for the prediction function to get the data from the sensors. On one hand, we still have Asset Planner for those 5 areas that were part of the pilot, but we have added a few other resources in here for the other areas that were added as part of version 2. We still have ECH over here. ECH was capturing the data, sending into the Azure IoT Hub, and that Azure IoT Hub was sending that raw feed into a Cosmos DB instance. We are getting JSON data. Cosmos DB is perfect to store data in that format. And then we have another function that was doing the standardization process. So taking the raw feed and putting that in a format that is going to be the same, or is going to be uniform for all the different areas in the museum. Whoops. So once that raw feed is standardized, it gets stored in Azure Cache. That allows us to just have the latest data for all the data points available to the prediction function. So instead of going and query this Cosmos DB instance, which can get expensive, we are just going to an Azure Cache and we have it ready to go, very quick access to that. The prediction function, the rest of the process looks pretty much the same. The prediction function calls that we created, or the two models that we created, I should say. We're still generating that prediction. That prediction, when a file is generated, it triggers that Azure function, sends it back to Azure IoT Hub, and back to ECEdge. So we had that working for a little bit, and I was very happy with the performance. Or it looked very promising. But unfortunately, we encountered another issue that was unrelated to all this infrastructure that we created. And the issue was related to the ECEdge system. So the ECEdge system, once we added more areas to the museum, it started to fail very often. It started to fail to the point that we needed to look into an alternative to ingest that data. So some of the areas of the museum are very, very big. There's a lot of data coming through, and it looked like ECEdge was having a hard time keeping up with that. So we had to remove it from the input side of the process, and we had to move all that ingestion into Asset Planner, into that API. Now you might be wondering, why didn't you do that from the beginning? The reason for that is that there was an additional setup that needed to happen, time-consuming setup for that raw feed from the sensors to make it into Asset Planner. So we were trying to avoid that work, but in the end, we were unable to do so. So this is the current version of the process. So we are going to Asset Planner for the input from the sensors. That prediction function still looks the same, still going to those machine learning models to predict the supplier humidity and the humidity in the room. It's generating a prediction that triggers that Azure IoT Hub update function. That gets sent back to Azure IoT Hub. We're still using ECEdge to send the predictions back to the museum. The reason for that is that the data that we're sending back is not as big as the data that we were trying to ingest. So ECEdge still works for that particular purpose. So we reduce a lot of the infrastructure so that we could use that API. So let's look at some numbers. So this is part of an analysis that was done last year for the first 3 months of the project. These are the numbers for one particular area of the museum called Museum 1. So October, November, and December. This first column is how many hours was the model on, or was the process on. How many hours was it possible for the process to be on, the percentage of those hours, and from the time that it was on, what's the percentage, or the humidity was satisfied, what percentage. So very good performance for like a first pass. December, obviously, winters in Chicago, if you've ever been, it's a little bit more difficult to keep that, but still for a first pass of the process, it was really, really good numbers. So this is a graph of the discharge air temperature for that same area. So for Museum 1, you'll see here this area on the left right here is the process not on. So you see that value hovering around that 58 degree with some spikes here and there, but for the most part, pretty much around the same value. And you can see a big difference here once we turn that process on. And you see it dynamically trying to adjust with everything that is happening within this particular area. So it's very cool to see that difference and trying to react, like I said, to everything that is happening. This is a graph of the discharge air temperature, so that predicted value versus the operating cost. So you can see here again, this is without the process being on. You can see the operating cost is obviously a little higher because we were probably cooling the air here. And once it turns on again, there's a correlation. If we let the temperature go a little bit higher, operating costs go lower, and you can see that across this particular graph. This is the discharge air temperature versus the energy usage. So right here in the center, you see this cluster in blue is when the process is not on because it's around the same temperature. And when the process is on, you see two clusters, two curves sort of right here. And then on the bottom, it corresponds to occupied versus unoccupied hours, because obviously the conditions are going to be different. So that's why there's that little grouping in there. But again, you see a big difference between the model being on and the model being off. These are the numbers for another area, a different area of the museum. And here is a perfect example of how, even though we are using the exact same process in both areas, some of them, the conditions are better suited for this, or it responds much better. So this was on more time than the other area. So 88% was the lowest. The other one was 72%, I believe. Humidity was still satisfied a pretty good amount of time. So again, very good performance for being the first pass or the first try. Again, this is the discharge air temperature graph. We see pretty much the same behavior as with the other one. Same thing with the operating cost. There's that correlation, and the discharge air temperature versus the energy usage. So we see those curves. We see 3 here. I believe this one was occupied versus unoccupied. I can't remember what the third one is at this point, but you just also see that cluster of a different color here for when the process is not enabled. Because one thing that I haven't mentioned is that the building engineers are still there. The building engineers still have sort of the last word in this particular process. So if they performing as good as it should, and they see some conditions outside of a particular range, they still have the power, they still have the ability to turn the process off and maybe take a look at what's going on in that area, or doing any sort of troubleshooting that they need to do. And they are able to turn it back on once the area has stabilized, or once they identify that there's some maintenance maybe that needs to happen, that needs to be done at a particular area. So this is a approximate timeline of how long it took us to set up this process. So from August of 2023, more or less, to October, so about a couple months with the data processing. So collecting, cleaning the data, analyzing, making sure that we understood all the relationships between the data points. The first version of the model, it took us about a couple weeks in October to set that up. So this is the first version of the model that we were trying to predict the discharge air temperature. The second version, where we created those 2 models for the humidity and the supplier humidity, again, took about a couple weeks in October. Then starting in November, we entered a process monitoring phase. So we monitor the performance of the process. We made some small logic changes as we saw the differences in between the different areas, and we made some tweaks, some of them very specific to a particular zone. And then we went back in May of 2024, so earlier this year, we added more zones, or we added the process to more zones of the area, and we did a little bit more of performance tuning. This project is sort of ongoing, so we are still keeping an eye on it, making sure that it's performing well. And we are also doing more analysis to see if we can get it as high as possible, if we can get it to be on as much time as possible without the building engineers having to turn it off, which is the goal, to only have it a small percentage where it needs to be turned off. So we're analyzing all these instances where they had to turn it on to try to figure out what happened, how can we make it better. All right, so let's look at some of the things that we used in this project. Again, in case that you have to work in a project like this and you're wondering what tools are available, what should you use, let's go and take a look at that really quick. So let me switch screens real quick here. So the first thing that we're going to look at is the Azure IoT Hub and that connectivity with Cosmos DB, because I think it's very, very cool and it's super, super easy to set up. I already have a route and an endpoint created here just so that I can do the next part of the demo. but I'm still going to go to the setup steps just so that you can see that. So if you need to automatically grab input from Azure IoT Hub and store it in Cosmos DB, let me take a step back actually. If you have an Azure IoT Hub instance, on the left-hand side, you have the hub settings, you have message routing, and then you have custom endpoints. If you see here, there's different options for you to store this data. So storage is the one that has been used from the beginning. So all the data will just go to a blob storage. You have Cosmos DB, which is the one that we're going to see in a second. But you also have event hubs. You have access to a queue or a topic, depending what your situation calls for, what you feel more comfortable with. Those are all the options available. So if we click on add, you'll see a screen that comes up. You have these same options that we saw on the previous screen. So Cosmos DB, event hubs, service bus, and then storage. And you can also use one of the built-in endpoints. You have to give your endpoint a name. Demo, I'm not going to create it, but just want to walk you through it. And the next thing that you have to configure is your Cosmos DB account. So obviously you need to have one created already. You need to have a database created in there as well as a container. So sensor input, a partition key template, and then you can choose the authentication that you are going to use for this endpoint, which is key-based. You can use a system assigned identity or a user assigned identity. If you are going to use one of these two, obviously, you need to make sure that this Azure IoT Hub has the right permissions to that Cosmos DB instance. Otherwise, you're not going to be able to create it. You can also create your route straight from this screen. But let's say that you created this this endpoint. Yes, I'm going to discard those changes. The other thing that you can do, let's say you create the endpoint and you don't create the route, or you need to create the route later, you can create the route right here. So the endpoint is telling Azure IoT Hub where to store this data. The route is going to tell Azure IoT Hub which devices are going to be stored in this particular, in this case, Cosmos DB instance. So here I'm saying that I'm going to send it to Cosmos DB. I already have an endpoint. I'm going to select that. Then demo route. Oops. And here you have the option to specify different data sources. So when you're dealing with these kind of devices, you can store or process telemetry message. You can connection state, but you can also do what's called a device twin change events. So that is what we set up on our case. So that is any change to any part of any data from this device, that is what's going to be captured. So once you specify that, you can also specify a routing query. In this case, it's just true. So that means that everything that comes from that Azure IoT Hub, it's going to go to that particular Cosmos DB instance. You can add a query that says only the data from this device is going to go into this Cosmos DB instance. So that is the setup that you have to do. Yes, I'm gonna get out of that. And the next thing that I'm gonna do, I have a very simple, super simple console app for this particular demo. So what it does is it connects with the Azure IoT Hub, and then it updates the data in one of the devices that I have. So let's go over here to the Cosmos DB instance. You'll see here this item was created before or earlier today because I wanted to make sure that everything worked fine. But if we hit load more, let's refresh. Live demos, you gotta love them, right? All right, let me change the value here to see if that might be the reason why it didn't update. And then let's go back over here. Still not loaded. Let me close. There we go. All right. So I guess that refresh wasn't working. But you see now, originally I had one item. Now I have 3 different items here. You'll notice that I did not have to do any coding for that data to flow seamlessly into Cosmos DB. So I think that is amazing, and that is great that you don't have to do any additional setup. You don't have to write any code in order to just capture that and send that information over. So this is what the data looks like. And like I said, it came without having to do any sort of coding, which is great. So that was the Azure IoT Hub plus Cosmos DB demo. Next thing that I want to show you is the Azure Machine Learning Studio, which is another tool that we use in this particular project. So this is what Azure Machine Learning Studio looks like. And this is a product that allows you to do a ton of different things with a machine learning world. So as you can see over here, you can create pipelines that do different kinds of cleaning in your data, that can run experiments. You have different algorithms that you can run. You can build a pipeline for like a recommendation model. You are also able to deploy your models to web service endpoints or batch endpoints, depending on what you need to do. And you're also able to create compute instances or compute resources to do your training. So you'll see here, I already have a compute instance, but let's look at the screens to create one. So obviously you will need a compute name, demo compute. I'll just walk you through the different options, different screens. And you have the ability to select either a CPU type or a GPU. So depending on what you need to do, you might need a GPU. Otherwise, you can stick with the CPU. And then you have here the machine size, the virtual machine size. One thing to keep in mind is that your Azure account has what is called a quota. So depending on your quota, you might not be able to create multiple computes for the same instance. But here it gives you a very good overview of what type of machine it is, the category, so memory optimized versus general purpose versus, I think, compute optimized is the other category. And that is going to help you choose the type of resource that you need. So depending on your scenario, so you see here a description of what this machine is best suited for. Here it tells you the availability, so how much quota do you have for that, and also the cost for that particular compute. In this case, it's telling you that it's going to cost you 18 cents per hour, which in a month is about $133, $134. That is something important to keep in mind, especially as if you're in a situation where you have to run the compute 24/7. Important to keep that cost in mind. So if I click next, this is a great thing that you are able to configure in these computes here in Azure Machine Learning Studio, is that you're able to say like, hey, if this compute, if you're using it only for training, for example, if this compute is idle for more than 60 minutes, shut it down. So for that cost that we saw in the previous screen, it's very important to have a setting like this. Then you go to security, you can specify what sort of access, you can lock it down or make it as restricted as you want. You can also specify if you want to provision the applications inside this compute with a script, or do you just want to go with default? You can add environments as well, add tags to your resources, kind of like you do with any other Azure resource. And then it shows you a screen with all the settings so that you can review and decide if that is what you want for this particular compute. Again, I'm not going to create it because that sometimes takes a little bit of time, but you also have other types of compute up here. So that availability is going to depend on the region that you're at and also your account. But you have compute instances. If you need a cluster, you can also create a compute cluster, Kubernetes cluster, attached computes, or just a serverless instance. The other thing that I want to look at really quick is called Automated ML. So this is kind of a wizard-like tool that you can use to create machine learning jobs and train your model with a particular data and create a model that you can then deploy, like I said, to a web service endpoint or some other web service batch endpoint. And there's another option I can't remember the top of my head, but let's look at what that. If you were to create a job here, demo, you can use a existing experiment. If this is part of the same experiment, you can just add jobs to that particular experiment. Summit experiment demo. You can add a description so that if somebody else takes a look at this job, they will know what you were trying to do there. And then you have the ability to select 5 different task types for the auto ML. So you can do classification. So that is a process, or if you're just trying to determine if it is a yes or no question, or you're trying to, you can also do different classes. So like it says here, blue, red, or green, you have the ability to do that. You can do a classic regression problem, kind of like the one that we covered in this particular project. Time series forecasting, you can do NLP, and you can also do computer vision here. So let's do select regression. I'm going to use this, even though that particular file is more suited for a classification problem, but this is just for the demo. So you select the target column. So what's the value that you're trying to predict, and then you can also specify. You can do what is called featureization. So if you want to specify that this particular column is numeric, you can do that here. You can do leave the auto if that's something that you want to do. So it allows you to do or configure different things. So this is more so if you know at least the basics of machine learning, this is a great tool to have. Obviously, you're able to do this in Python, do this training in a notebook or some other way. You can also do this if you're using ML.NET, you can do that as well. But if you prefer this kind of visual interface, this kind of wizard interface, this is a great tool to have. Other configuration that you can do is the primary metric. So what you're going to use to evaluate the results. Again, very familiar options if you've done machine learning projects in the past. You can ask to Machine Learning Studio to explain the best model. So what that means is that it's going to give you a ton of other data that you can access. Like, for example, which features were the most important when doing a particular training. That way you can see, okay, maybe the next experiment, I only want to run with these 4 features, for example, or these 2, if that is something that you have to do. Enable ensemble stacking. So if you want to do you want to do ensemble stacking, like voting ensemble or something like that. You also have the ability to specify if you don't want to use a particular model. So If you click on that, for example, if you don't want to use a random forest in your experiment for some reason, because it's not performing well, or like I said, some other motivation, if you don't want to use a decision tree, you can specify that in your experiment as well. So I'm going to cancel out of that. You have other information here that you are able to say, okay, if you've run this experiment for 60 minutes, for example, that's all I need. I don't need you to run longer than that. And then you can also specify the validation type. So if you want to do k-fold, you can specify here. You can leave it on automatic. And you can also specify if you want to do if you want to split your training data into training and testing so that Machine Learning Studio can evaluate the models. You can specify that from here, for example, in 15. And then once you click next, it gives you, hang on, let me see, what am I missing here? What value am I missing here so that we can move on? Train test split. Oh, no, let me change that to this. There we go. Because I had the wrong column selected there. So next is the compute. So you can specify the compute instance, for example, that you created earlier. You also have the ability to create that from here. If you wanted to do serverless, you can specify in here as well. It gives you, again, some of the same information that we saw in the other screen. So you have a ton of different options depending on what you think you will need for this particular experiment. And you can specify if you're using serverless, the number of instances that you want to use. So all that configuration, you click next, it starts running a job. And here I actually started a job earlier, but it looks like it's not done yet. So let's say that this particular job, this particular experiment was completed. You can click inside of this and you can see a ton of information in here. So here you can see all the models that were used, and you can see what the result for that using this particular model is. Then if you are happy with it, you can click on that. And if you click on deploy, for example, you have those three options where you can do a real-time endpoint, a batch endpoint, or just a regular web service. If you do the deployment into a, if you do the deployment here as a web service, it is a little bit more limited than if you did it from a, like a command line or some other tool. So that is one thing to keep in mind if you're going to do this. But if you're not concerned about that, or you don't need to configure a ton of these of the values or the settings here, you can just use this. You can use this screen to deploy them and start calling them. You can call them obviously from Postman, or you'll be able to call them from any other tool that you use to call any other API. It'll be basically available through an API if you did something like that. You can explore other information as well. So the output from the jobs, I guess in this case, I can't show it because the job is not done, but if I ask to explain the best model, it will give me a ton of different metrics and a lot more information so that I can make a decision of whether I want to use this experiment as the model in my process, or if I need to run another experiment with different configurations so that we can, we can get to the predictions that we need. So that was Azure Machine Learning Studio. Next is Microsoft Fabric. So this is a product that came, it's relatively new. And let me pull this screen over here. And this is a product that came out last year. And what this is, what the intention of this Microsoft Fabric is to be a one-stop shop for all the data that you have whether it's in Azure or in some other cloud as well, that you have one place to just go look at that data, do different processing, and processing out analytics with that particular data. So we used this, or we looked at Microsoft Fabric at one point, because if you remember, we were storing our data for the raw input, but also our prediction in our predictions. We were storing it in Cosmos DB at one point, and we wanted to be able to query this data or look at this data as just a regular SQL table. So that's what we were trying to do. So Microsoft Fabric has the ability to, or has a feature that is called a mirrored Azure Cosmos DB. And this is super simple to set up. So you click on that mirror Azure Cosmos DB, you'll see it will show you sources. You click on that. All you need is your Cosmos DB endpoint and your account key, and you are able to create a replicated copy of your data. So I already have one here. So once you set up all that, you will get this screen where it says, there's a replication running at the moment, and over here you have two options. You have the option to access that Cosmos DB instance, but you also have this SQL Analytics endpoint. And what that gives you is exactly what we wanted. So over here, you will see that there are a bunch of, in this case, they show us tables, but these are just basically the collections, the different containers that we have in a Cosmos DB instance. And you will see that if you click on any of those, it shows you the data as a regular SQL table, which is something very familiar. Now, there is a caveat that if you have nested objects, so this column, for example, let me see if I can expand it. Don't think so. Let me see. No, that's just starting. But anyway, what this column has nested JSON objects in there, so it still looks like JSON data. So that's not something that it can do out of the box at the moment. You will still have to do some processing if you had to run some queries here. But the rest of them, you can look at them like in any other like any other SQL instance. So for example, if I want to do from AIC, so let's do the prediction input. Whoops. So if I run that query, apparently I can't run SQL queries. There we go. And of course, since it's a live demo, it's being a lot slower than it normally is. So while that is running, I am going to just change this to be, we'll just run a different query. So last updated. So you have the same sort of intelligence that you see in your SQL server. So let's just get those two columns instead of everything else. And you see that that's just regular SQL syntax instead of what you have with Cosmos DB, or just like the natural Cosmos DB query language. So a great thing to have, like I said, if you have data in different places, let's say you have some data in AWS and data in Azure, for example, Microsoft Fabric has connectors to different clouds, to different data sources. So you can connect all those into a workspace, for example, and just look at all your data in one place. So if you have a similar requirement or you're trying to do something like that, this tool is a really good thing to have. All right, so those are the tools that we used in this project. So now let's talk about the things that we learned. So this is not just in this project, but just other machine learning projects that we worked on. And first of all, the first thing is that very important to consider in machine learning projects is that stakeholders are even more important in these projects than regular software development projects. We know that having a champion of a project is very important regardless of any software development project, but it's even more important here because in machine learning, some of the deliverables are not going to be something that is going to make sense or something that is going to be demoed really easy at the end of the sprint. If you work on a regular project, so for example, you're adding a button to the screen, that is something that you can demo at the end of the sprint. In here, if let's say you're just cleaning data, you're doing different analysis, this is not this technically you could demo it, but it might not make sense and not a lot of people are going to be interested. So you might have, there might be certain reactions like, what do you mean it's taking it a month to clean this data and do all this analysis? So you need someone that is going to be a champion for the project and is going to make sure that everyone knows that the project is still on track, even if they cannot see anything actionable or any deliverables from this particular project. So very important to consider. Another thing that is very important is to define clear goals. So I have seen machine learning projects that just disappear or are stopped because there's no definition of what success means. What does it mean for this machine learning project to be successful? In this example, we're trying to be more energy efficient. Energy efficiency is one of the goals. So we need to be able to set certain goals of, for example, say we're going to try to reduce the energy consumption by 5% in the first try. Let's say that, that's something that we all agree on. That is going to be very important in case that, again, we have somebody that's coming from outside the project or somebody that is starting to look at the project and is wondering, hey, that doesn't make sense. I would expect this to be saving 10%. But if we have something that we all agree on that is going to be enough for this first part, we can then look at it again. And for a future phase of the project, let's say we do go to 10%. But otherwise, if nobody knows what that means to be successful for that project, there's a big risk to all that work to be thrown at the board because there's a perception that it's not working as good as it should. It's very important to keep in mind. It's very important, obviously, to know the data, know the relationships between the different data points, how they can affect each other. That's going to help you get to a solution a lot faster. You're also going to be able to troubleshoot issues with the process a lot faster. If you're able to pinpoint, oh, I know why this is happening. This particular value is outside of the range, or this particular value is really weird. Where is that coming from? It might also allow you to identify issues that are outside of the process. So we had an instance where our process was doing what it was supposed to do. We had an area that was very warm. Our process was trying to decrease the temperature, but for some reason, the temperature was not decreasing in that particular area. So we found out that there was something wrong at the building that needed to be fixed, and it was not part of our process, or it was not an issue from our process. So knowing all those relationships are going to be very, very important in these projects. Make sure that if you're dealing with sensors, or if you're dealing with infrastructure like that, that you evaluate that infrastructure early on in the project. In here, because of the state of the project when we came in, we were not able to kind of take that step back, but that is something that we would have definitely saved us some time kind of down the road. So if you're able to identify all those different naming conventions that we stumbled upon once we started adding more areas, if we had found that earlier, we could have addressed it in a different way. Not that big of a deal, but it's gonna save you some time if you're able to look at all the infrastructure first. And then finally, machine learning, AI projects, we have to be very careful, not only about the implementation, but also how do we release it. And we have to make sure, we have to consider the impact that that particular project is going to have, whether it's an internal project or with our clients. What is it going to look like? Our people are going to be receptive of that particular project or that particular change or not? In technologists, we always get very excited about the possibilities of a new technology, but for people that are outside of that, and they might not be as receptive, like I said, to a particular change in their day or in their process. So keep that in mind. Obviously, we're not at a point where we can just create these processes and just leave them to their own devices. So make sure you have room in your process to keep humans in the loop. As I mentioned earlier, the building engineers at the museum are still able to turn the process off if it's not performing properly. So make sure that you have, like I said, a space for that in your process. And then finally, make sure you apply safeguards in your process. For example, if you got to make sure that if you're not getting data from the sensors, don't try to create a prediction. And that's something that we have in our process. Because if we're not getting the data that we need, the prediction that we're going to generate is probably not going to be a good one. So things like that, make sure that you account for those scenarios. Make sure you protect that process so that it's safe, especially if you're dealing with something a little bit more critical. In this case, it's not as critical. It's not like someone's life is gonna be affected, but some of these processes deal with things like that. So keep that in mind. So if you found this interesting, if you're working on a similar project and you have questions, again, about the tools that we use or the approach that we used, I'll be more than happy to connect with you. You have my socials right there in the left QR code. And also on the right-hand side, you have another QR code that can take you to a page to schedule time with me. If you want to set up a call, like I said, to just chat about it or any technology really in the Azure AI ecosystem, I'll be more than happy to do that. I do other presentations on the topic. And then finally, a big thank you again to all our sponsors, our online streaming sponsor, Proximo 3, our digital sponsors, Locodera, Riata Consultancy, and Cubix. Remember, if you are attending this session or if you are at the Scottish Summit, you can use the hashtag Scottish Summit 2024 to share this in other amazing sessions that are going to be here. So that is it for me. I hope that you enjoyed this presentation. And again, reach out if you have any questions.